Hey there, so this video, I want to briefly address assumptions in repeated measures, assumptions in repeated measures, all right? So, luckily for you, most of the assumptions are exactly the same. So that's good, all right. So equal n, believe it or not, actually, the way we're doing repeated measures here, it ensures we're going to have equal n across treatment groups, okay? So it just will, if we're missing a value on one of those dependent variable blocks, the whole case gets dropped out, and that's just how we're doing repeated measures in this particular class. So there are ways and other techniques that we can do repeated measures where that would not be the case, but for us here it's fine. So basically equal n across treatment groups or conditions we're taken care of here. All right, so that's good. Independence of observations, well, obviously we're repeating cases, over different treatment groups or across time. So we don't look for independence of observations there. What we would look for is going to be whether or not, let's say, people are related to each other in the sample. So for instance, if I'm doing a study on romantic jealousy and its effects, I may not want to have people who are dating each other in that particular sample, because if one person in a couple is jealous, there's a good chance the other person might be as well. So we'd want to ensure we don't have people who are dating in that type of analysis. So in that type of data set. So, and that's kind of your typical, so usually we're just going to assume we've met independence of observations. So that's good, all right. So just like in regular ANOVA, are people related to each other? Is there something we should know about the data? Same kind of drill. Generally, we're going to assume we've met independence of observations. So equal n's taken care of for us. Independence of observations, same thing as we've been dealing with before. Normality, what we're going to do is take a look at a normal distribution within each dependent variable block, and I'll show that in a different video. So that's going to be normality. And then also homogeneity of variance. We're going to take a look at the variances within each dependent variable block as well, and just make sure they're all within a 10-to-1 ratio of each other. Okay, so there is a new assumption though, and the new assumption is technically it's called compound symmetry, but what we're going to do is I'm going to have you assess that using something that's referred to as sphericity. So generally, if you have sphericity in your data, then you've met compound symmetry. So I want you more to focus on this idea of sphericity. And the Howell textbook talks about sphericity, so take a look at that, and I'll talk about it right here. So when we're talking about sphericity, and again, if we have sphericity, we've met the assumption of compound symmetry. All right, so if we have sphericity, we've met compound symmetry. So let's just focus on sphericity. So the idea of sphericity is it has to deal with how these dependent variable blocks are related to each other, and essentially the correlations across the dependent variable blocks all have to be approximately equal to each other. All right. So let's say we have in our example we're working with 3 time points. With 3 time points, there's going to be a correlation between time point 1 and 2. And time point 2 and 3, and time point 1 and 3. All those correlations need to be approximately equal to each other. If they are approximately equal to each other, then we have met the assumption of sphericity. Well, we have sphericity, and therefore then we've met compound symmetry, right? So again, we're making sure we have sphericity, and if we have sphericity, then we've met the assumption of compound symmetry. So that's how that kind of flows forward. Let me give you a quick example. Let's say that this is a classic example that a lot of textbooks use, and you'll read it here and there. But let's say you're doing research on children and word acquisition. Children and word acquisition. It's more of a developmental psychology type of study, so word acquisition. And you assess how many words kids know at the age of 4, at the age of 6, 8, 10, 12, 14, 16, et cetera. Well, in that, if you start taking a look at the correlations with how many words kids know between the ages of between 4 and 6, 6 and 8, 8 and 10, 10 and 12, et cetera, and then you start looking across things, like you have 4 and 8, 4 and 10, 4 and 12, 6 and 8. So you get the sense of taking a look at all those dependent variable blocks. You, in fact, would not have sphericity. In other words, especially with word acquisition in children, just because a kid knows a lot of words at the age of 4 doesn't necessarily mean that they're going to know a lot of words at the age of 12. Why would that be? Because of environmental factors that kick in. So, so generally when we work in developmental psychology, and if we're working with word acquisition, lo and behold, we probably will not have sphericity, and therefore then we violated compound symmetry, and that would be a problem. Now, let me show you just a couple things in the reader here, just what we're going to look at, and then there'll be another video later on where I'll actually go into more detail about this. But I do want to focus on, and this is the you don't need to see me anymore. This is the time example in the reader, and the only reason I'm showing this right now to you is because I want to point out how we're going to assess sphericity. And what we're going to do in any of this output in repeated measures is we're going to focus on this thing right here, this thing referred to as the greenhouse geyser epsilon. The greenhouse geyser epsilon. Don't look at this. Don't look at that. I know it's under Mauchly's test of sphericity. And many of you will, like a moth to a flame, you will go, oh, here's my test, and here I'm going to use this. Don't do that, okay? Again, don't do that. What I want you to do is you're going to focus on this greenhouse geyser epsilon, value. And this value, and I'll go back through this in another video, this value needs to exceed a value of 0.7. This value, see this value of 0.685? See that is that greater than 0.7? No, it's not. So that's a problem. And then if I went to another example where, and I'm not even don't want to spend that much time on this video doing that, but I was going to go to the other example we're working with, but I'll do it in another video. But again, how are we going to test for compound symmetry? How are we going to test for sphericity? We're going to use this greenhouse geyser epsilon value. See, epsilon, and there are a few of them here, but the one I want you to focus on is this. So think greenhouse geyser. So again, sphericity, think greenhouse geyser epsilon. Greenhouse geyser epsilon. It's greenhouse, it's geyser, it's epsilon. How do we test for sphericity? The greenhouse geyser epsilon. All right, there we go. I just wanted to put that buzz in your ear so you're familiar with it. And the next video, I'm going to go ahead and walk us through a little bit more on these assumptions and more stuff on the output in our examples in the reader. All right, thanks.